This video is the Probability Performance Task Practice Guide. These problems are very similar to the problems that are in your performance task. So if you're having any trouble with the performance task, by the time you watch this video, you'll be ready to go. Alright, let's take a look at the first problem. Maria is considering playing a game at the fair. There are two different games to choose from, and it costs $3 to play a game. Their probabilities associated with the games are given in the table. What is the expected value for playing each game? Now, to get expected value, you follow this procedure. You multiply each value by the probability of getting that value, and then you just add all those up. That's what expected value is. Alright, each value times the probability of that value. So for game 1, which I will just call G1, the expected value should be, alright, so I'm going to take each value and multiply by the probability. So there is a probability of 0.45 for a value of $3. There's a probability of 0.3 for a value of $2. Wait, I made a small mistake here. The $3, we're talking about losing $3, so that's negative $3. Okay, so 30 cents, no, not 30 cents, 30% probability of winning $2, and we have a 25% probability of winning $5. Alright, so this calculation should give me the expected value for the first game. So I'm just going to put that in my calculator. Okay, that comes out to be 3.2. So that is the expected value of playing this game. Alright, that 3.2 means $3.20. That's the expected value. Alright, and that means if many people played this game, on average, they would win $3.20. Now, let's take a look at game 2. For game 2, I'm going to do the same thing. 30% chance of losing $3. You know what? I think I forgot to put the negative 3 in there when I did my calculation. I just did 3. I didn't do negative 3. That was a bad mistake. Negative 3. Expected value is 50 cents, not $3.20. Alright, that was the expected value. Alright, so now I'm going to do the same thing for game 2. 30 cents for losing $3. There is a I should stop saying 30 cents. 30% chance of losing $3. There is a 35% chance of winning $2. And there is a 35% chance of winning $5. Alright, I'm just going to put that in my calculator and see what the expected value is. This time I'm going to be sure to put the negative sign in. I'm getting $1.55. So that means if many people played this game, on average they would win $1.55. Game 1, if many people played, on average they would win 50 cents. Okay, so obviously if Maria decides to play the game, which game should she choose and why? Clearly she should choose game 2 because on average, people who play game 2 are winning $1.55. That's $1.05 more than people win on average playing game 1. Alright, I just went and typed that up, what I just said. Maria should play game 2 because people who play game 2 win $1.05 more per game on average than the people who play game 1. Alright, and looks like that was it for this particular question. Alright, so let's move on to the next one. Tanisha. What's Tanisha up to? Tanisha is considering investing in a new business. In the first year, there is a 0.3, that's a 30% probability that the new business will lose $15,000. That's a lot of money. There is a 25% probability that the new business will break even. They won't lose or gain anything. And there's a 35% probability that the new business will earn $5,000 in profits. And there is a 10% probability that the new business will make $10,000 in profit. So, what is the expected value if Tanisha invests in a company for a year? Well, we just talked about expected value. So hopefully you remember that expected value is probability times value plus probability times value plus probability times value plus probability times value. So it seems like there were 4 probabilities and values. All right, $15,000, 0, 5,000, 10,000. So probability in value 1, probability in value 2, probability in value 3, probability in value 4. So let's just fill that in and see what we have. So the first probability is 0.3, and that's for $15,000 value. Oh, okay, losing $15,000. So let us not forget the negative sign. All right, the second probability, there is a 25% probability that the business will break even. So that'll be times 0. The third probability is a 35% probability that the new business will make $5,000. And the fourth probability is the 10% chance of making $10,000. Okay. So you can just put all that in your calculator. This was negative. It disappeared on me. That's what messed me up last time. I'm just going to put all this in my calculator and see what the expected value is. Alright, I'm getting negative $1,750. Okay, so on average, if this situation happened over and over again, on average, people would lose $1,750 every time. So should Tanisha invest? No, because people on average lose this much money on the investment. Okay, so I've written it up just like that. No, Tanisha should not invest because people lose an average of $1,750 a year on this type of investment. Okay, what else you want to know? Now, so we're sort of rewriting the situation. Imagine that Tanisha's initial investment was $7,500, And imagine that instead of having an expected value of negative $1,750, imagine that her expected value was positive $1,500 a year. How many years would it take her to earn back her initial investment? All right, so she paid $7,500 and now she's gaining $1,500 each year. So how long would it take her to earn back that money? Well, that's just a simple division problem, isn't it? We just take that initial investment of $7,500 and divide by 1,500. All right, that should tell us how many years it will take. All right, 5 years. Okay, all right, looks like that's it for that question. All right, let's move on to the next one. Marco is playing basketball, and he is about to try for a three-point shot. It's a close game with little time left. Alexander, a player on the other team, has a choice to make. Should he foul Marco and let him take a free throw, or should he let Marco try for the three-point shot? Obviously, we're assuming that Alexander's not in a position to simply block Marco, which would be ideal. But he's not in a good position for that. But he can he can push him or yank his arm or something illegal. That's all he could do. Anyway, the reason why Alexander is thinking about this is because Alexander knows that Marco makes his three-point shots 20% of the time, but he makes his free throw shots 50% of the time. All right? So he knows this, and he's trying to figure out point-wise, a three-point shot is obviously worth 3 points. But he's less likely to make it, but it's worth 3 points. Which should he choose? The way to figure that out is to do expected value and figure out, on average, which situation would give you more points. And whichever one will give you more points on average over time, that's the one that has the best chance of winning. So that's the one you would choose. So let's do our expected value calculation again. So remember, whenever you do your expected value, you're always doing a probability times the value plus probability times value. All right, so we have these two possible values. Either, this is for the three-point shot. Either he makes it and gets 3 points, or he doesn't make it, so he gets 0 points. So those are the two values. If he makes his three-point shots 20% of the time, then obviously we're talking about probability of 0.2, and we'll multiply that by the value of 3 points for this three-point shot. But that means 80% of the time he misses. So that's why we're doing 0.8 times 0. So this should give us the expected value for the three-point shot. Okay. All right, so 3-point shot. Expected value equals. Obviously, multiplying by 0, that's not going to give us anything. So really, it's just a matter of 3 times 0.2. So that should be 0.6. Okay. I'm not sure why it says 2 free throws. He's only getting 1 free throw, not 2. Okay, so these are the probabilities mentioned in the problem. So the expected value would be 50% chance that he's going to get the 1 point, and a 50% chance that he's going to get no points for the free throw. Again, the 0 is just going to wipe this term out. So it's really just 1 times 0.5, which is 0.5. So free throw, the expected value is 0.5. All right, so it seems like if this were done over and over again, then you're going to get more points from the 3-point shot scenario. On average, you're going to get 0.6 points if you do the 3-point shot over and over again in this situation. On average, on a free throw, you're going to get an average of 0.5 points. This is more, so that's going to give you more points. Now, Alexander does not want that to happen. Alexander wants fewer points to be scored. So Alexander really wants to make Marco go for the free throw and get, on average, fewer points. So how does Alexander make Marco take the free throw instead of taking the 3-point shot? Well, he's got to foul Marco for that. So should Alexander foul Marco or let him try for the 3-point shot? So again, Alexander is on the other team. So Alexander should foul Marco and let him try for the free throw, because on average Marco will score fewer points shooting free throws than he would shooting 3-point shots. And Alexander wants Marco to score as little as possible because he's on the other team. All right, that is the end of this particular question, the basketball question. All right, let us move on. All right, I think there are 2 more questions in this performance task. Number 4. A game at the fair involves a wheel with 7 sectors. 2 of the sectors are red, 2 of the sectors are purple, 2 of the sectors are yellow, and 1 sector is blue. Okay, all right, got it. Now, landing on the blue sector will give you -4 points. All right, so let's type some of this into, all right, so we have -4 points. Okay. All right, that's the blue sector. So there's only 1 blue sector. So the probability of randomly landing on that is 1 out of 7. You know, we're always talking about target over total. So for the blue, there's 1 blue out of a total of 7. So that's going to be the probability for the blue. All right, so the probability of hitting this -4 value is 1/7. Okay, now let's see what's next. Landing on yellow gives you 2 points. So we're talking about 2 points, but probability, there are 2 yellow sectors. So the probability of landing on yellow is 2/7, 2 out of 7. All right, landing on a purple sector will give you 3 points. Okay, so again, there are 2 purple sectors, so that's a probability of 2 out of 7. Okay, and then landing on a red sector will give you -1 point. Okay, there are 2 red sectors, so again, that's a probability of 2 out of 7. Okay, so there we filled out the missing values, all of the values with their probabilities. Now, if you take 1 spin, what is your expected value? Well, as we've seen on every other problem so far, we know that expected value is going to be the probability times the value plus the probability times the value until you've done all of the probabilities and values. So we're going to do 1/7, all right, times -4, probability and value. And we're going to do 2/7 times 2. And we'll do 2/7 times 3. And we'll do 2/7 times -1. So add all that up, and that should be our expected value. Okay, I'm getting 4/7, which is approximately 0.57. Okay, that is the expected value. All right. So that means this is not a fair game in the sense that a fair game is defined as a game that has an expected value of 0. So what changes could you make to the assigned outcomes to make the game fair? So what changes could we make to our little system here of values? We really can't change the probabilities. We're sort of stuck with the spinner that we've got. But we can change these numbers. So let's play around with these numbers and figure out how we can make them give us an expected value of 0. Because that would make it a fair game. All right, and no, it would not be acceptable just to let all the values be 0. All right, I'm not accepting that as an answer. So, but let's do this. I'm going to do this one last. I'm noticing that this is just 1/7. So I'm going to save this and let it be a negative value, whether it's -4 or -5 or -6 or -7. I can just make this be whatever I need it to be to cancel out everything else. So how about we let this one be 0, okay, and we'll let this one be 1, and we'll let this one be 2. Okay, if we do that, then the 0 just is already gone. We don't have to worry about that. But here, if we do, if we look at this pair right here, okay, so we have 2/7 times 2. All right, so 2 times 2 is 4, so that's going to make 4/7. Meanwhile, 2/7 times 1 is just 2/7. Okay, so 4/7 plus 2/7, that's going to make 6/7. All right, so everything else is 6/7. So if we made this -6, all right, because I'm looking at this 6/7, and I want this to be -6/7. All right, because that way I know that these will cancel each other out and make 0. Okay, so there it is. This would be a system that would work. So let's just remember how this went, so we can write it down. But it's basically going to be the -6 must be for the blue one, and then everything else will go in order. So let's just write that down. Landing on the blue sector will give -6 points. Landing on a yellow sector will give 2 points. Landing on a purple sector will give 1 point. And landing on a red sector will give 0 points. And we've already proved why that would make it a fair game. We'd get an expected value of 0. Maybe I should write that down as well, just to finish off my little proof here, e equals 0. Alright, so that's it for that question. So I'm pretty sure that number 5 here is the last one in our performance task. Okay, so Latron is playing a game in which a box contains 6 chips with numbers written on them. Alright, so here's a little picture of that scenario. 2 of the chips have the number 1 on them, 2 of the chips have the number 2, another has the number 3, and another chip has the number 4, just like this. Latron must choose 2 chips. If both chips have the same number, he wins $3. What else? If the 2 chips he chooses have different numbers, then he loses $2, negative $2. So that's where these values are coming from. So of course here we need to write down the probability of each one of these values so that we can figure out the expected value. So we need to do target over total. So we do need to know how many total possibilities there are. So here are some possibilities. It could either be a 1 and a 1. Alright, that's one possibility. Or it could be a 2 and a 2. Okay. So, by the way, those are the 2 possibilities of where they're the same. So now let's talk about the possibilities when they're not the same. Okay, so when they're not the same, it could be 1 and 2. Or it could be 1 and 3. Or it could be 2 and 3. Okay. Or I feel like putting the 2 and 3 down here. So it could be 2 and 3. What have I not done yet? It could be, what about with the 4s? Okay, it could be 1 and 4. Or it could be 2 and 4. Or it could be 3 and 4. So that's it. These are all the possible combos. Now, there's a total of 8. And I did give you that hint, but now I've shown you exactly why it's 8. So there's a total of 8. So if I want to earn $3, I need to have them be the same. So target over total, all right, the probability of that is 2. All right, so the probability for this one, there are 2 ways to win the $3. Either have it be a 1 and a 1 or a 2 and a 2. So there's 2 of those out of a total of 8. Now I wrote that off to the side because this reduces down to 1/4. Okay, so that's the probability of getting $3 is 1/4. Now how about the probability of losing $2? Okay, so if we're talking about losing $2, there are 6 ways that could happen. Alright, 6 ways, again, out of a total of 8. So that reduces down to 3/4. Okay, it's messing up a little bit there, but you can still read it. Alright, so now we're ready to do our expected value. So you've seen this several times during this performance task. So by now you're very familiar with the fact that expected value is always going to be the probability times the value. And then probability times that value. Add them up and that's your expected value. So I'm just going to put this in my calculator. I'm getting negative 3/4. So on average, Latron would lose 3/4 of a point every time he played this game. Okay, so based on the expected value in the previous step, how much money should Latron expect to win or lose each time he plays the game? Well, all right, so if these are dollars, I said points, I guess I said points, I should have said dollars. So let's convert this to a decimal so we can talk money. 3/4 is 0.75. So this is negative 75 cents. So Latron should expect to lose an average of 75 cents if he played this game many times. 75 cents per game if he played this game many times. Now, what value should be assigned to choosing two chips with the same number to make the game fair? Okay, well, to make the game fair, remember that means the expected value has to be 0. So this should be easy because we only have two possibilities. Either they're going to be the same or not the same. So the way it was, we won $3 if we got a match. So this is the number that we're talking about changing. All right, is that number right there. So we're basically saying, what does this number have to be? The value that we win if we get a match. That will make this a fair game. That will make the expected value equal 0. So keep an eye on that. I'm going to turn this into an X because we don't know yet. We have to find the value that will make the expected value 0. So instead of having 1/4 and then a 3 in there, I'm going to have 1/4 and then X. Alright, and this other one is still 3/4. Okay, and that's -2. But if it's going to be a fair game, the expected value should be 0. So all we really have to do is solve this equation for X. So I've got 1/4 X. I'm going to leave that like it is for now. Let's see. -2 times 3 is -6. And that's really what we're going to do. We're just going to multiply the numerators. 3 times 2 is 6. 4 times 1 is 4. Alright, because it's a -2, that's going to make this whole thing negative. But I'm not going to put plus negative. I'm just going to put minus, because that's what's the proper way to write. Alright, so we'll just put minus 6/4. So I need to keep going and solve this for X. So we should add 6/4 to both sides. And yes, I could reduce this to 3/2. It doesn't really matter. But, you know, I could have reduced it. So I'm going to add 6/4 to both sides. So now I have 1/4 X equals 6/4. Okay, so now to get X by itself, I need to get rid of this 1/4. The easiest thing to do is to multiply both sides by 4. Alright, that's why these 4's will cancel each other out, and at that point the 1 doesn't really matter. These 4's will actually cancel each other out as well. So that's just going to leave me with X equals 6. So that's the answer to the question. If we made the value of getting two chips the same, if you won $6 for that, then that would make this a fair game, because overall, on average, you would break even. You would get $0 if you played this game over and over again. And I think that is it. That was the last question of this practice performance task. So hopefully you understood each of these examples because they are very similar to the problems that you are asked to do in your performance task. So if you can do these, then you will easily be able to do those. Good luck on your performance task.